Now we'll move on to the steady state fire, which is the more commonly used fire in any smoke calculation. There is a common misconception that a steady state fire will grow to a certain size and then keep burning at that rate due to limited fuel or oxygen. The approach is to look at the largest size that the fire is likely to reach and to design the smoke control system as if it was indeed this size. It is necessary to consider the impact of sprinklers as well. This approach has been one that's been adopted in the UK and indeed many countries all over the world for the past 35 years. Now, where do we find the information for our design steady state fire? There are a number of guides where you can obtain relevant information. One such source is BR368, Design Methodologies for Smoke, Heat and Exhaust Ventilation Systems. In table 3.3 in this document, you can find some information on design fire sizes. Here are some examples extracted from this table 3.3 in BR368. Another source for design fire sizes is CIBSE Guide E, and here are some typical heat release rates per unit area that you can find in that document. If the items that may be on fire are not represented in the BR368 table, then the design fire size can be calculated as follows. We need to know some basic information. Firstly, we need to know the heat release rate density of the material that may be on fire. That is the heat output per square metre. We also need to know how big the fire may reasonably be expected to grow to in terms of its physical size. And finally, we need to know the proportion of the total heat output that will go into the plume as convective heat. The heat release rate densities for various items can be obtained from databases held by the BRE or the NFPA or from other organisations that do research in this field. A common value that is used is 625 kilowatts per square metre, and this is often used for sprinklered fires involving unknown or unspecified contents. 625 kilowatts per square metre is used as it is considered to be conservatively high. The physical area of the fire is related to either the sprinkler spacing or to the size of an isolated package of fuel, such as a reception desk in an otherwise empty atrium. The Smoke Ventilation Association gives various accepted conservative areas for fires in different types of premises. For most normal risk premises, a fire is expected to be contained to a size no larger than the space between 4 adjacent sprinkler heads in any array. That is, if the sprinklers are set in an array with 3 metres between the sprinkler heads in each direction, then the maximum size that the fire will be expected to grow to will be 3 metres by 3 metres, which is 9 square metres. There may well be sprinkler heads other than the 4 immediately surrounding the fire that are also discharging water, but they'll be wetting the surrounding area, stopping it from burning, and the fire will be contained to the space within the 4 heads around the point of ignition. This containment of fire is expected in about 95% of cases, and the confidence level of 95% is usually deemed sufficient. As mentioned earlier, there may be situations where you have to carry out a number of scenarios to identify which is the worst case. For example, in an airport atrium, you may have a few potential different fire sizes, and you may have to work them all out to determine the highest mass flow rate of smoke and the highest temperature of the smoke layer. There may be a fire in one of the shops in a mall, and there could be a store located directly in the atrium, and there could be a covered cabin with sprinkler protection. In this case, you may have to analyse all the design fires to determine the highest mass flow rate of smoke, and the ventilation system must cope with this, as well as taking into account the temperature of the smoke layer as well. Once you've identified the design fire size, you need to determine the convection portion of this. Not all of the heat from a fire goes up in the plume as convective heat output. When a fire burns, it will give out a certain heat release rate, which is measured in kilowatts.